You know, filters are one of those fundamental tools for pulling information out of data. We use them for everything, right? From processing audio to building the giant convolutional neural networks that power image recognition. But here's the thing. Today, we're seeing more and more data that doesn't live on a nice, neat grid. It lives on these complex, sprawling networks. So let's dive into the core building block for making sense of it all, the graph filter.
And this really is the central challenge for researchers today. All those powerful filters that we've spent decades perfecting for things like time series signals and images, they just fall apart on these irregular data structures. You can't just take a standard convolution and slap it onto a social network or the connections in a brain. The whole idea of a shift or a delay, the very foundation of those filters, it has to be completely reimagined from the ground up.
And believe me, this isn't some niche academic problem. The world of modern data is absolutely built on graphs. We see it everywhere: the web of connections between people on social media, the functional links between different regions of our brains, even the atomic bonds inside a molecule. It's the hidden structure of our power grids, the communication pathways and sensor networks, and it's the engine behind the recommender systems that suggest what you should watch or buy next.
So here's the game plan for this explainer. We're going to break it all down. First, we'll talk about why we even need a new kind of filter in the first place. Then, we'll introduce the foundational graph convolutional filter. From there, we'll look at the wider landscape of filter types, see how these simple blocks build up to modern graph neural networks, and finally, check out their massive real-world research impact. All right, first up, the new data frontier. Let's talk about why our old toolkit just isn't going to cut it anymore. So, the heart of the problem is this. Traditional signal processing assumes everything lives on a regular grid-like structure. We call this a Euclidean domain. Think about the pixels in an image. They have a clear up, down, left, and right. Or the samples in an audio file, which follow each other in a perfect line. Graphs, though, they're totally irregular. A node in a social network doesn't have a fixed number of neighbors in some predictable pattern. And that irregularity just shatters the core assumptions our conventional filters are built on. Okay, so we've got the problem. What's the solution? Well, that brings us to the graph convolutional filter, or GCF. This is the absolute cornerstone of modern graph signal processing.
Now, before we can even build a filter, we need a way to shift a signal across the graph. That's the whole job of the graph shift operator, or GSO. At its core, it's just a matrix. Could be the adjacency matrix, maybe the graph Laplacian, and it basically holds the blueprint of the graph structure. When you apply it to a signal on the graph, it does this beautiful local information mix. It just takes a weighted combination of the signal from a node and its immediate neighbors. This is our new shift. It's the graph equivalent of a one-step time delay.
And here's where it gets really elegant. This new abstract idea connects right back to the classics. A standard time series filter, it's actually just a GCF operating on a super simple graph, a directed cycle where every node is just a point in time. And on that graph, what does the graph shift operator do? It just moves the signal to the next time step. It becomes a time delay. This is brilliant because it shows that graph filters aren't trying to replace the old methods. They're a powerful generalization of them. So once you've got the GSO, the graph convolutional filter itself becomes pretty intuitive. It's really just a shift and sum operation. You take your original signal, then you take your signal shifted once by the GSO, shifted twice, and so on, maybe up to k-shifts. Then you just take a weighted sum of all those shifted versions. And mathematically, what you end up with is a polynomial of that graph shift operator matrix. Let's make this concrete. Imagine we're calculating the output at just one node. What happens? First, we grab the node's own value and multiply it by our first filter weight. Easy enough? Then we look at its direct, one-hop neighbors, aggregate their signals, that's our first shift, and multiply that by our second weight. Then we do it again for the two-hop neighbors, and so on, all the way out to k hops. The final output for our node is just the sum of all those weighted pieces. This design gives GCF some incredibly useful properties for any researcher. They're local, meaning the math for one node only depends on its k-hop neighborhood. That's perfect for distributed systems. They use parameter sharing. That same small set of weights is used for every single node in the whole graph, which is what makes them so scalable. They're also permutation equivariant, which is a fancy way of saying it doesn't matter how you label or order your nodes, the filter just works. And crucially, this all means they're inductive. You can learn a filter on one graph and apply it to a completely different one. That's a real game changer. Now, the GCF is amazing. It's the workhorse, but it's not the only tool in the box. One size doesn't always fit all. So let's explore the broader filter landscape for a minute. The main limitation of GCFs, because they're built as a polynomial of the GSO, is that their frequency response is, well, a polynomial. This is totally fine for a lot of tasks, but sometimes you need to model something more complex, maybe with a really sharp cutoff. To do that with a GCF, you might need a super high-order polynomial, which can get computationally expensive and even unstable. And this is exactly what's motivated the development of other more flexible filter types. So as a researcher, you're faced with a classic trade-off. You've got the GCF, which is efficient, it has linear complexity, and it's transferable. Great. Then you have rational filters, which can create much more complex responses, but you pay a price. The complexity jumps all the way to cubic. And then you have something like node-varying filters. They're super flexible, with different parameters for each node, and they keep that nice linear complexity. The catch? They lose transferability. They're stuck on the graph they were trained on. The right choice really just depends on the problem you're trying to solve. All right, now for the really big leap. Let's see how these fundamental filter concepts are actually used to build the powerful deep learning models we all know as graph neural networks.
The next level of abstraction up from a filter is the graph perceptron. It sounds fancy, but it's actually incredibly simple. You just take the output of your linear graph filter and you pass it through a nonlinear activation function, like a ReLU, at every single node. That's it. That simple step of adding nonlinearity is what unlocks the ability to stack these things and learn much, much more complex patterns.
And a graph neural network is exactly what it sounds like from there. It's a network of these graph perceptrons. You create a deep architecture by just cascading them, one after another. The output of that first perceptron becomes the brand new input signal for the second one, and so on down the line. It's this deep, layered approach that lets GNNs pull out incredibly abstract and powerful features from both the graph's structure and its signals.
This really brings us to the core idea, and the source paper for this explainer puts it perfectly. It's so easy to get lost in the complexity of GNNs, but they say popular graph convolutional neural networks, GCNNs, can be seen as no more than a nonlinear graph filter built by nesting a GCF into an activation function. In other words, at their heart, they're just our simple GCFs wrapped in an activation function and stacked on top of each other.
And this isn't just theory. If you look at some of the most famous GNNs out there, you see they are just specific flavors of this framework. The standard graph convolutional network, or GCN, it just uses a simple first-order GCF. Graph Sage, it does the same thing but adds a normalization step. The graph isomorphism network, or GIN, same idea, but it makes the weight on the self-connection a learnable parameter. They are all just clever variations on the exact same theme.
Okay, so we've gone from the most basic building block all the way up to deep networks. Let's bring this all home and look at where these tools are making a real-world impact in research, from theory to actual application.
What's so amazing is how these filters and GNNs are being used all across the map in both classical signal processing and cutting-edge machine learning. In the SP world, they're used for things like denoising signals on sensor networks or detecting anomalies in power grids. Over in ML, they're the engine behind state-of-the-art node classification. They help fill in missing data for recommender systems, and they even classify entire graphs, like figuring out the properties of a molecule just from its structure.
So when you take a step back, what this all comes down to is that graph filters provide this beautiful, unifying framework. They are the fundamental, principled, mathematical building block that connects a simple task like smoothing a signal all the way to these incredibly complex, state-of-the-art graph neural networks. If you understand the filter, you understand the foundation of network AI. And that leaves us with a final, really exciting thought. At their core, filters are how we extract patterns from data. That's their job. So if we now have the tools to design custom filters for literally any network you can imagine, the question isn't if we can find new patterns anymore. The question is, what incredible new discoveries are just sitting out there, waiting for a researcher like you to design the right graph filter to finally uncover them?